So now we start solving exercise sheet number 3. It's really called 3.1 because I will try to use the same numbers here, the same numbering as Martin in the lecture. And since the section 3 will be divided in more than one, in some subsections, you know, the first subsection is about systems of linear equations, and that's what we are talking about now. Well, it's a little special here. The first exercise, 3.11, is about such a system of linear equations with already a number of 4 different unknowns. The specialty is not only that I right away use the matrix and vector notation, but this is, I think, this is okay for you. You know what it means. It's just a presentation which gives you the coefficients of the 4 different equations in matrix and vector form. You know what it really means? It means something like we have 1 times, let's say, x1, first unknown in this equation. Then we have minus 2 times x2 plus 1 times x3 plus no times 0 times the 4th unknown, and then equals, this is what the vector gives you, the right-hand sides of the equations. So this equals 2, and then next equation accordingly would be x2 plus 3 times x3 equals 2, and so on. Okay, so this is just a short representation of such a system of equations. That's clear, I think. The other specialty here is that we are using the so-called F3, which is a field, as you know, a field, something very special in mathematics, or you could say unconventional, at least for general purposes, because we only have a set of 3 numbers, you know, these 3 elements. So the only numbers that occur in fact are 0, 1, 2. And so this must be some kind of periodic behavior connected to this field. Don't be irritated if I use negative numbers here. Of course, the so-called opposite is defined also in a field, but the first task will be to convert these numbers according to the algebra table or the arithmetics table of this field to always get elements out of this selection, 0, 1, 2. Okay, I'll try to explain. If you have difficulties with putting up the these, I call them field algebra tables for addition and multiplication, there's a trick. This is the hint given here. The trick is to use modulo 3 arithmetics, and I guess you know what is meant. It means if you get a number outside the range of, you know, 0, 1, 2, you just you make it like this. You make a cyclic transformation. It's like if I say, okay, 0, perhaps counterclockwise. It's more mathematical. Let me see. Oh, my pen has. That's a problem. Sometimes my pen does not react anymore, and that's really bad. I must pause the recording just a second, please. That's really that's a pity. So sorry for the little accident. My pen is just out of function. Now it works again suddenly. I don't know why. Anyway, what I wanted to do is make a circle like 0, 1, 2, and then always go in this case counterclockwise. You know what I mean? I always go around this circle. So for example, here, by adding these numbers, this is easy. 0 plus 0 equals 0. 1 plus 1 equals 2. That works fine. And also 0 plus 1 is 1. 0 plus 1 is 1. This is, of course, symmetric. Okay. But then if I add 2 plus 2, I would get 4. And since 4 is out of range, I just say, okay, 0, 1, 2, or, well, how should I say? I just look how far is it outside the range. So like, did I get it right? 0, is that correct? 4? Yes. So you could say 0, 1, 2, 3, 4. You see what I mean? I just go around this circle and say 0, 1, 2, 3, 4. So 3 is 0 again, and 4 is 1 again. It cycles. So instead of 4, I'm putting 1 here. Let's look at the multiplication table. Again, this is easy. 0 times 0 is 0. 0 times 1 is 0, and also 1 times 1 equals 1. But then 1 times 2 is fine. It equals 2. But then 2 times 2 equals 4 again, and as you know, 0, 1, 2, 3, 4. I circle around and my result is 1. You see what this is? This is a kind of a cyclic algebra using modulo 3 arithmetics, nothing else. But it's very interesting by itself to use a number system which has only 3 elements. So now this is what I put here also. You see the cyclic replacement. Where the lower line gives you the actual values to be used, and this gives you the original values. If they are out of range, you have to put them into the range again. So it's quite a simple method, actually, to do it. Now, regarding this system of linear equations, we first have to transform it or convert it. That's what's written here. By first transforming all coefficients to F3. I could also say converting to F3. And then let's do this. Look here. I look at these numbers and then I find, okay, everything that's inside 1, 0, 2 is fine. I don't change it. But -2, look here, corresponds to 1. -1 corresponds to 2. And that's it, or no, -1, -2, yes, and -3 corresponds to 0. So that's all I do. I put the first line gets 1, 1, 1, 0. Yeah, this -2 replaced by 1. And then I think Martin didn't use this, but I do it. I use this vertical bar to denote the extended coefficient matrix, you know? And I also denoted the lines with Romanian numbers 1, 2, 3, 4, Roman. Okay, then this represents all the equal signs in the 4 equations. You know what I mean? So that's just a separator. It doesn't have any other meaning. So anyway, if we go ahead, we have, where is it? Here. This 0, 1, the 3 must be replaced by, look here, by 0. Okay, and then -1 gets 2 again. That's the third line. So this third line should be, let's see, 2, 0, 1, 0. And the other is then 2, 0, 1, and also 0. You know that 3 and -3 in the end are the same number, namely 0. So that means we have twice the same equation. And that's it. That's the conversion to our field F3 as a starting point. And this is just a symbolic notation for matrix A, vertical bar, vector B. So that's one standard notation for compact notation for equation systems like this. Now, we don't have so much time left, but I will try and present you already now the so-called Gauss-Jordan elimination, which is an extended version of the Gaussian elimination method, you know. The only difference is, while the classical Gaussian elimination has the so-called echelon, the upper echelon form as an end state, the Gauss-Jordan elimination method goes one step further. So what it does is, in the first step, it eliminates in the first column. That's what Gauss also does. And in the second step, it eliminates in the second column. While Gauss does the elimination only in the lower triangle, the Gauss-Jordan elimination also eliminates, not only below the diagonal, but also upward. So also here, and here, if you can, you should produce zeros everywhere except for the diagonal. That's the idea of, you could say, a full elimination, which is called Gauss-Jordan elimination. Because in the end, if you get your coefficient matrix to diagonal form, this is more than you could say this is an extended echelon form. It's like an upper and lower echelon form at the same time, called diagonal form. Then here is it. Here it is. And then even you have ones on the diagonal. This is a so-called unit matrix. Then you can just read your solution on the right side. If it's a unique solution, you can just read it out. In this case, we have a zero row, which means we must introduce some solution parameter also, but that's only the last step then. So what I wanted to show for now, until time is over, is the first is the procedure as such. And this is my kind of notation. You don't have to use it. You can use your own. It's enough if you understand what I mean if I put these arrows and numbers here. So what I mean is the following. When I start out using this this elimination method, I mark my first diagonal element. I start in the upper left corner and I end in the lower right corner, ideally. Okay, it means the whole procedure orients itself or is oriented on the diagonal. I mark this as a tool. So this is my tool in order to eliminate all the numbers in the first column. I do this by using exclusively the first row. So the first row is my tool, or in the broader sense, but in a special sense, this number on the diagonal is my tool. It's my tool which I use to eliminate these numbers if they are not zero. I make them zero. And what do? I use the addition method to say I am allowed to add a multiple of this row to each other row in order to eliminate one of the coefficients, and then in the end to eliminate unknowns from these equations. So that's what I do. And in this case, I just add the first line to the third. You know why? This is what I mean with +1. I add this because by chance now 1 + 2 = 0. That's the special thing about field, okay? Field F3. Usually I would have to take the, this row times 2 and then subtract it from here to get a 0 here. Like 2 - 2 × 1 = 0. But this time we have field algebra, which means we don't even have to take a multiple. We just add the line here because by chance it's the case that 1 + 2 = 3, but cyclic replacement, in the end it equals 0. So I get my elimination here. Let's just do it, okay? So this one plus this, usually I go the arrow backwards. So 2 + 1 = 0 here. 0 + 1 = 1. 1 + 1 = 2. 0 + 0 = 0, and 2 + 2, remember, is equal to 4, but outside of range. So cyclically speaking, it must be 1. So here's the 1. That's the first step, to eliminate here. Here I don't have to eliminate because this is already 0, but here I do the same thing. And since this is exactly the same row, meanwhile, after conversion, you see that it results also in the same row as here, namely 0, 1, 2, 0, and 1. So that was the first step. The whole first column has been eliminated. And then I proceed, only then I proceed to the next element on the diagonal, which is this one in the second row this time. So I see that my other students are not yet, have not yet arrived. So I just allow myself to take some more minutes, perhaps 1 or 2 minutes longer. Anyway, so the same thing again, just look and see if you understand what I'm doing here. I leave away the arrows now and I just annotate what I'm doing. I subtract the new working row, which is number 2. I subtract it here, here, and here. Why? Because this is number 1, 1, 1. And to eliminate, of course, this time I have to subtract my my second line, where we must be a little bit careful because subtraction is not really defined in the field algebra. I would usually have to replace it by an addition of the opposite number, etc. But let's do it the simple way, okay? So anyway, if I go here and say 1 - 0, that's what I do, gets 1 or stays 1. 1 minus 1 gets 0. That's my intention here, to eliminate. You see, this is Gauss-Jordan already, because Gauss wouldn't even have eliminated at this place, but Gauss-Jordan also goes to the upper half of the matrix to eliminate. I mean, from the perspective of the diagonal, this is the upper half, this is the lower half, okay? So then, also here, 1 minus 0 stays 1, 0 minus 0 is 0, and 2 minus 2 equals 0. So we can use regular subtraction if we just always keep in mind that we have to replace numbers that are out of range cyclically. So, and then here, the same, 0 minus 0 is 0, 1 minus 1 is 0, this is my elimination, then 2 minus 0 is 2, 0 minus 0 is 0, 1 minus 2, that's important now, 1 minus 2 is negative 1, but that is cyclic to 2. You see, must be replaced by 2. I have some sound here, some noise, so I must mute you for a second. Okay, now and then that's it, almost, because you see again in this row the same thing takes place. So also this time this row gets identical. I do this systematically, so that's why I hesitate to make this a 0 row. I could have done this before already here. I could have said, okay, we can subtract the third line from the fourth, and then we get a 0 line. But I do this systematically so that it has to wait for a while. And now I'm here, and now I eliminate accordingly, okay? To get this one, you see, this is the trick again. I add the third line, the third row, because 2 plus 1 is 0 again. Starting here, 1 plus 0 is 1, 0 plus 0 is 0, 1 plus 2 is 0, 0 plus 0. Okay, nothing else happens because 0 plus 2 equals 2, that's it. This is an alternative way to take this times 2 and then subtract the third line, but that's the third row. But that would be yeah, quite fun, because it results in exchanged numbers, and then in the end it transforms to this form again. This is just a remark. Don't just ignore it. Okay, it's the best to ignore it because we don't need it actually. So last step now, but this time really, let me see. This is already eliminated. Here, to eliminate, I subtract the third line, and so finally I get my 0 row here, and practically it's the last row, which is with generally if you get a 0 row, you should push it down to the last row. What does a 0 row mean? Well, this is the so-called clean 0 row. So it's not corrupt. It's not. It doesn't contain a contradiction, because if I read it out, it means that 0 times first unknown, 0 times x1 plus 0 times x2, etc. So 0 in the end equals 0. And since this is a true statement, it means that all it means is that one equation is missing. So we have 4 unknowns, but only 3 valid equations, where we can read the solutions of the first 3 unknowns just here. We can just read what's written here, because this is a unit matrix so far. That means that that x1 equals 2, x2 equals 2, and x3 equals 1 in this field F3 algebra, while the fourth unknown, called x4, can be chosen freely. It can be chosen freely because its corresponding equation is just missing. It's fallen out of the system. That's what you do. And then in the end, we have this as the general solution for this underdetermined system of linear equations, as it's called. It's underdetermined because its so-called rank is equal to 3 only and not 4. The rank is defined by the size of the submatrix that we were able to put in diagonal form. This is what we reached here, as you see. Okay, so due to this row or this equation missing in the end, we have a free solution parameter lambda element F3. Don't forget, we only have 3 values that are allowed. So in the end, it's not infinitely many solutions, but it's only 3 of them, because this is a very reduced number system. So after all, 2, 2, 2, 2, 2, 1, 0, 2, 2, 1, 1, 2, 2, 1, 2. These are the 3 vectorial solutions of the whole system of linear equations. Perhaps a final remark. It's a special topic to how to handle such cases where we have 1 or more zero rows, and then to introduce solution parameters in an appropriate way. In this case, it was quite simple. In other cases it may get a little more complicated. So I think I really extended more than enough, and it's time for me to say goodbye for now.